Mhm. Okay. So in this lecture and probably the next couple of lectures, we'll start studying a new model, a mathematical model that will help us represent data, understand some properties whenever you're given a data. And graphs, whatever you're going to see about graphs, this model is so ubiquitous that it will just travel with you for the next like 15, 20 years. Everything that you see can be modeled as graphs. And that is the basics of graph theory is what you will study in like the next 2, 3 lectures. Okay? So what are graphs? You can think about these as some sort of a discrete mathematical structure. Some structure that can be used to model data, or used to model some real-time systems. Let's call this real-time systems. So what systems are these? We need to see. So before understanding what graphs are, or mathematically defining graphs, since we have not seen graphs before, let's see where we use these. We use them almost every day in our lives. It's just that we didn't realize that these were graphs. Okay. Okay. So the first place where graphs were actually defined was in the year 1736, somewhere in the 18th century. It was defined by this mathematician from Switzerland, Euler. Yes, he was the first person to identify graphs. So in what context did he come across graphs? So there were a few people who lived in the city of Königsberg, which is a city in Prussia, which is modern day Russia. And this city had 7 bridges. So there were land masses, and there were rivers flowing through the city, and these land masses were connected to each other by bridges. Right? So there were 7 bridges. So even today, this city exists, though in a different name. And now there are only 2 bridges. So a few of them have come down. So these 7 bridges existed, and people posed this question. So suppose someone wanted to start from one location, let's say somewhere here, like wherever the mouse pointer is, and they wanted to cross every bridge only once, and they wanted to return back to the same location. And they had to cover all the places. So you can think about this as some postman coming to you, he wanted to deliver post. So he starts from one location, somewhere where the mouse pointer is, maybe between 4 and 7. Okay, so this is where the post office is. He's going to start here. So he can take the bridge 4, go to the other side, deliver post. Then he could enter this center area via the bridge 2. Then he could cover that landmass, then take the bridge 6, cover this landmass, and then go back, take 5, take 1, and so on. So he has to cover every location. He has to come back to the place where he started from, and he has to cross every bit exactly once. So this question people had posed, whether this is possible. And this is what is written here, right? Whether a route existed that would traverse each of the 7 bridges exactly once. And Euler demonstrated that the answer to this question is no, that it is not possible to travel exactly once across these bridges and visit every location. So this, we will see a proof of this, not in this lecture. We'll have to develop the theory behind graphs. But this is a very simple question, which is not framed in the language of graph theory at all. Okay? But this whole question can actually be framed as a question in graph theory. For that, we have to understand what graphs are, right? Which we will see. So the history of graph theory dates back to the 18th century in 1736, and this is the first problem, first theorem to be proved in graph theory. Let's see some more examples that we see every day. So another example is the problem of a knight store. I'm not sure if you've seen this. So here is a chessboard, and the question is, you have to place a knight on the chessboard that visits every square on the chessboard, and it is to come back from wherever it started. And the only moves that the knight can make are those legal moves, right? The 3 steps that it can take. And here is an animation, right? You can see how the knight moves. And so this is a 5x5 chessboard, and the knight actually covers all the squares on the chessboard. So is this possible? Can you do this? So for 5x5, here is an animation that shows that it is possible. Can you do this for 6x6, 7x7, 8x8, and so on? So this is called the knight store. there is a lot of history behind it. So if you're interested, you can go ahead and read it. Although this question was posed later on in terms of chess, this was actually the actual question was framed in the 9th century by Rudratha. So this is called Rudratha's tour. So this is one question that we can actually frame as a question in graph theory. We will see how to frame this. I'm just showing you like some examples. Okay. And then we have all used social media, right? So you have all used Facebook. You make friends on Facebook. You unfriend people on Facebook. So how is this data actually stored on Facebook's end? Right? So for example, you may have like some 100 friends. And every day you log into Facebook, you see these messages, right? Your friend liked this brand. Your friend watched this video. She posted this comment or he posted this comment. So this data is actually stored as a graph, which is called the social graph. Right? So it's a graph where it includes data about all the people on Facebook. And then if 2 of them are actually friends, then you have to somehow represent that data. A is friends with B. And you must also remember that this structure keeps changing, right? You might find new friends, you might unfriend old friends, and so on. So it's a very dynamic structure, right? And this graph is actually maintained at Facebook's end, and that is how they give you notifications. So this graph is called a social graph. This is one example where graphs are actually used. And for those of you who are actually following some sports championships, you may have seen some tournaments, right? So these tournaments, what they do is there are a set of players, like some, let's say 100 players who start. So this is the graph corresponding to the Wimbledon. So every player plays against a certain player, and in that round, one of them wins, the other loses. The one who loses is eliminated. That is one tournament. It's called an elimination tournament. And in the end, these people play against each other, and finally you see a person who wins. And so this graph is called the tournament graph. Right? So this information is very helpful. So if ahead of time I give you who you're going to play against, you can develop a strategy, right, to play and win. So this graph is called the tournament graph. We'll actually study this graph, and this graph has many properties. But for this, I have to tell you what a graph is, but at least you can imagine, right? Whatever is drawn here is a pictorial representation of how the tournament proceeded from start to finish. Right? There can be other tournaments. For example, everybody plays everybody else. It's not an elimination tournament, and then you give some points, and based on the points, you decide who's eliminated at which stage. Some sort of a league. And so this is one place where these tournaments come up. So after the tournament is over, IBM or some data analysis company might take data from this, understand what happened, and they may give it to the players, right, which will help them to improve. So another place where graphs come up in everyday life are the web, right? So you might have browsed Wikipedia before. So if you just look at graph theory, you type graph theory in Wikipedia, page opens up. And that page has links to several other pages. And that page will have links to several other pages. So how is this data actually stored? Right? So this is stored as a graph where you represent the pages by points. And there is a connection between 2 points if there is a link from this page to that page. Right? So this is called the web graph, the World Wide Web graph. Some people call it the www graph. So here is one graph that represents Wikipedia, all pages on Wikipedia. So this has so many topics, right? Social, political, and stuff. So you can click on one of them. And then that page loads up. Yeah, it's not loading right now, but you can try this. So, and it will show you the various links it has to other pages. And then you can traverse to one of those pages. And then you can see that there are some other pages and so on. Okay. So this is one place where graphs are actually used. So graphs actually can be really helpful to model data, right, or model real-time systems, like for example, road networks and so on. But to understand what properties of the data we can learn, right, we must first learn to model data as a graph. So what is a graph? So these are some examples of graphs. But what is a graph? So generally, a graph is depicted by 2 sets. So it's denoted by the letter G. It has 2 associated sets. One is V, the set of vertices, and E is the set of edges. So I'll tell you what these are. So here is an example of a graph. So this is called, so these circular ones are called vertices or nodes. So we'll call them vertex, plural is vertices. And there is a, you draw a line between two vertices this way, right? A line between two vertices, that's called an edge. Right? So V is a set of vertices and E is actually pairs of vertices. Okay? So each edge has two vertices associated with it. So let's try to give another example. This one. So how many vertices are there in this graph? So this is a graph G. Let's call this 1, 2, 3, 4. Right? So you denote this by VE. The cardinality of V is 4. The set of vertices is 1, 2, 3, 4. And then there are edges. Okay? So you denote the edges by 1, 2, 3. Is this clear? So graph is just a structure that has two sets associated with it. One is the set of vertices, which you can think about it as representing data, and the edge that represents relationship among the data. Right? For example, if you look at the Königsberg bridge problem, then these are like the bridges. Let me just go back to that page. This one, right? So there are land masses 1, 2, 3, 4, and a bridge is represented by that. So there is a bridge between 1 and 2, which is here. There is a bridge between 1 and 4, and so on. Is this clear? Is the definition of a graph clear? The one on the right is an example of a graph that models the scenario on the left. So the question that people asked is that, can you, let's say, start from any of these vertices, these 4 vertices, come back to the same vertex without walking on any of these edges more than once. So this we have all done in school, right? Where they give you a picture and they ask you to retrace the picture with pencil without lifting the pencil. But sometimes you are able to do it, sometimes you weren't. This is an example where if you do it, start from 1 and you ask the kid to retrace it with a pencil, without lifting the pencil, it's not possible. Or you will have to go through 1, 2 again, twice. So this way, you can model graphs. Some examples of graphs are what we saw. So if you think about the World Wide Web graph, right? So the vertices are all the pages, and you draw an edge from page A to page B if there is a link from hyperlink from page A to page B. Similarly, in the social network graph, how Facebook shows it, is if all people are all vertices, and if 2 of them are friends, then there is an edge between them. So these are some examples of graphs that we have seen. Okay. So we know what are vertices, we know what edges are, and this graph, there is exactly one edge. So edge is just a pair of vertices, right? So you could have 1, 2, 1, 2, and so on, things like this. Right? This is also possible. So maybe I'll use a different color. This is still a valid graph. And a graph where there are no multiple edges between between a pair of vertices is called a simple graph. No multiple edges. And if multiple edges are allowed, like for example, so G is a simple graph, let's call this G prime. So G is a simple graph. And graph with multiple edges is called a multigraph. Is this clear? Like what are graphs? What is a simple graph?
Could you say about the multiple edge ones?
Sure, sure. So, for example, let's take this road network. Okay. So let's say that this one is Chennai and this is Mumbai. So there can be, for example, multiple roadways, right, between Chennai and Mumbai. It's not necessary that there has to be exactly one. So there are
Yes.
applications where between two vertices itself, you may have several edges. There are several paths, right? There are several ways to reach two from one. You can think about it that way. So a graph is said to be a multi-graph if there are multiple edges between some vertices. If there's exactly one edge between every pair of vertices, that graph is called a simple graph. Is this clear?
Ma'am, then how is G a simple graph?
Oh, okay. Yeah, that was it. Maybe I'll draw another example. Let's keep this one. This, I think, is, I put this yesterday. Yeah, that is right. Yeah, here there are two edges. Okay, so I will call this G and this G. Let's give this a name H. Just to show.
Is multi-graph a graph?
Yes, yes. So multi-graph, simple graphs, these are all kinds of graphs. Right? When you say graph, it's like the most general object. You just need a set.
Edges are a set of ordered pairs of.
No, right now there is no order, right? So far we have not seen any order. What is the order? So 1, 2, and 2, 1 are the same here.
So 1, 2, and 1. You cannot in a set. You cannot have 1, 2 two times, right?
Right. So so that is why it's called a multi-graph. So graphs generally we don't write them as sets. We just draw them as pictures. So it's like a graphical representation. So when you write them as sets, so the question is asking is if 1, 2 appears 4 times and 1, 2 appears only once, how will I know the difference, right? When you write it as a set.
Yes, ma'am.
So right. So in general, what they write down when you have to describe the graph, because this graph is simple, I wrote it this way. Otherwise, what you have to actually write down is this is the set of edges where 1, 2 has multiplicity 2, 2, 3 has multiplicity 1, 3, 4. That is how you write a multigraph. So a multigraph is described as a set of edges together with the multiplicity of each edge. Okay.
Okay, ma'am.
Correct. So yeah, initially, so this is for the purple portion. For the orange edge that is added, you'll have to write that the edge set of the graph is 1, 2 with multiplicity 2, 2, 3 with multiplicity 1, and so on. But throughout this course, we will be interested only in simple graphs, at least as far as I. So we will talk only about simple graphs, but it's good to know that these graphs exist. So somebody asked, right? So one of the students asked, how different is 1, 2 from 2, 1? It is very natural that in some applications, you will want to model a 1, 2 being different from 2, 1. For example, the flight network, right? Let's say that 1 is Chennai and 2 is Mumbai. There might be a flight from Chennai to Mumbai, but there may not be a flight from Mumbai to Chennai at a certain point. Right? So that is where the notion of directions in graphs come up. So we will look at directed graphs. So a directed graph is also a graph, sometimes called as digraph. It's also a pair, E, where V again is a set of vertices, but E now is a set of directed edges. So what do we mean by that? So there is, let's draw a graph here. So this is a directed graph. So there are 4 vertices and there are 5 edges. So this is a directed graph. So in a directed graph, every edge has a direction. So every edge here is an ordered pair. Right? UV. So this means that this edge is starting from U and ending at V. So this is like from U to. Just like simple graphs, there are directed multigraphs. So is the concept of directed graphs clear? So a graph where there is a direction associated with every edge. So if you think about this flight network, right? So there can be flights that, I don't know in which case this would arise, but there can be flights that start at a city and then come back to the same city, something like that. So to represent such examples, we have this notion of an edge starting at a vertex and ending at itself. So this is called a loop. So we may come across this. I'm not sure if it's like very crucial, but it's good to know that loops can also exist. Okay, so are things clear so far? Yeah, if there are questions, please ask. Yeah, there is no point moving forward.
Ma'am, you can have loops in non-directed graphs as well, right?
Yes. Yeah, so you can
Okay,
have things
yeah.
like this. This is also possible. Okay, so we've seen undirected graphs. So these graphs are, so general graphs without directions are usually called undirected graphs. And graphs with direction are called directed graphs. And there are directed simple graphs, directed multigraphs, undirected simple graphs, and undirected multigraphs. Okay, so now in these applications episode, right? These stories episode. Whenever, so for example, here, even in the Königsberg bridge problem, whenever there is a bridge between these two land masses, you drew an edge between them. Right? So these two are connected. Similarly, these two are connected, these two are connected, and so on. So this is called an adjacency relationship. So what do we mean by that? So whenever you have a graph G, so from now on, we will use the letter G to denote a graph. And when we say a graph G, we mean that there are two associated sets, the set of vertices and the set of edges.
Hello, ma'am.
Hi.
Ma'am, simple graphs can have loops, right?
Yeah, okay. So generally when we say simple graphs, we don't talk about loops. So there is a special term for that. I didn't want to introduce more terms. So a graph with loops is called pseudograph. But you won't see this in the lecture. But I will just write it down.
Okay, ma'am.
Pseudographs. So when we say a graph G, we'll have to define the set of vertices and we'll have to define the set of edges associated with it. And let's take any pair of vertices UV in the edge set. So this is represented by E of G, that is the edge set of the graph G. Then we say that U is adjacent to E. It's close to E in some sense, the term adjacent means, and they are connected by a line. So you say that the vertex, for example, this 1, 2, 3, 4. Let me just delete the loop because I don't want to talk about loops here. So 1 is adjacent to 2 and 3, but okay, let's talk about undirected graphs because I have to come to directed graphs. So let's name 1, 2, 3, 4. So 1 here is adjacent to 2 and 3. 2 is not adjacent to 4. Okay. Is the notion of adjacency clear? Similarly, if you look at the edge, let me just draw some graph. So 1 is adjacent to 2 and 1 is not adjacent to 4. Similarly, if you look at the edges, right, let's call this edge E1, this edge E2, E3, E4. So there are 4 edges. You say that the edge E1 is incident on 1 and 2. These are just some terminologies. So if you look at the edge E is equal to U comma V, E is incident on the vertices U and V. So it's like E connects U and V. Right? So these are some important terminology that you know. So all of this is terminology. No big thought process here. but to actually solve the questions, the Königsberg problem and stuff, so we'll need to know some terminology. So now we'll probably see the most important terminology that you use. The rest of your lives you'll probably use it. It's called the degree of a vertex. Right, so 1 is adjacent to 2, 1 is adjacent to 3. Right? So 1 has 2 neighbors. So a neighbor, you said 2 is a neighbor of 1 because there is an edge between 1 and 2. You said 3 is a neighbor of 1 because there is an edge between 1 and 3. So now the degree of a vertex is the number of edges. Let's say degree of a vertex V is the number of edges incident. And the degree of a vertex is usually represented by degree of V. So what is in this graph? Let's call this graph H. So in H, what is the degree of 1? So how many, I should not have drawn this in the right. So how many edges are incident on 1?
2.
2, right? So yeah, this is one of them and this is one. And how many edges are incident on 2? 2 of them. 3 has degree 3 and 4 has degree 1. Is this clear? Is this example? This should be like crystal clear. No doubts. Yeah, so some more examples maybe. So there are so this you can try as an exercise. We can take a couple of minutes and try. Then we'll see some more terminology once you're comfortable with this. Right, so this vertex has degree 3, this has degree 3, 2, 1. Is this correct? I hope I didn't mess up. Right? So now this vertex, right? This vertex that has degree 1 is called a pendant. It's just hanging in there. So nobody asked me, is this, so now let me just erase all these degrees, otherwise I won't know which is the vertex number and which is the degree. So any vertex of degree 1 is called a pendant. So now is this a graph? This whole thing? This is fine, right? So there are like 6 vertices and there are a few edges. 6 edges, 5 edges, 7 edges. So this is also a graph. So a vertex can have degree 0. And this vertex is called an isolated vertex. So any vertex of degree 1 is called a pendant and a vertex of degree 0 is called an isolated vertex. Is this clear? Okay. So you can try some more examples of graphs and try to determine their degrees. So now let us see the first theorem in graph theory. Let us consider a graph G, is VE. So there's a set of vertices and there's a set of edges, which is an undirected graph. And let's say this graph has m edges. So So what I mean by that is the cardinality of the set E is M. So this is a simple graph. Right, right now, let's just say that there are no multiple edges. And what can you say about the sum of the degrees of the edges of all the vertices? So sum B degree of loop. Is this notation clear? Like what we mean by that? So here we want to ask degree of V1 plus degree of V2 plus degree of V3 plus V4 plus V5 plus V6. Also, usually we use V1.
2 into number of edges.
Right. Okay, so what is this? Let's try to estimate.
2 into number of edges.
Yes, that's right. Yeah, that's the right answer. Does everybody can also see that? So every vertex, if you look at the degree, so if you look at this edge, this contributes degree 1 to this vertex and degree 1 to this vertex. Right? If you look at this edge, it contributes degree 1 to V4 and degree 1 to V5. So every edge contributes 2 to this summation. So the sum of the degrees of all the vertices is 2 times the number of edges. Is this clear? So this theorem is called the handshaking lemma. So this is exactly the number of handshakes you will see in a group of like n people, if there are n vertices, assuming that nobody shakes their own hand. Total number of handshakes. We represent this, like if they shake a hand, we draw a line with them, and then the total number of handshakes. So the sum of the degrees of the vertices in any graph is 2 times the number of edges. This also works if the graph has multiple edges. Okay, so now let's see a simple example. This lecture will be like super basic, but next time we'll see like some real applications, like hard applications of graph theory. So if I have a graph G that has, let's say, where the cardinality of V is 10. So there are 10 vertices, and the degree of every vertex is 6. So what is the total number of edges?
Thirty.
Okay. So in any graph on with 10 vertices, each vertex having degree 6, there will be like 30 edges. Okay. So now we know that the sum of the degrees of every vertex has to be 2 times the number of edges. Now let's say I have an undirected graph. So this is the first one.
Ma'am, and the handshaking lemma will only work for simple graphs, right?
So what would happen if it's a multiple graph? It's fine, but it's just that when you say number of edges,
No,
you'll have to count that set with multiplicity.
there can't be loops, right?
Yeah, so I didn't want to get
It's
into
still
this.
valid.
So what is the degree of a loop, right? So suppose there is a loop here. Let's put this in some other color. Okay, suppose there is a loop here. Now what is the degree of 3?
4.
Well, so we actually, when we define the degree of a vertex, we always define it to be the number of edges incident on it. But if there is a loop, it contributes degree 2 to the vertex. That's how we define it. That's because generally when you look at this particular edge, right, the starting point, it contributes 1 to the degree, and the ending point contributes 1 to the degree of that vertex. But unfortunately, the start and end of the loop is the same vertex, so it contributes 2 to the degree, 2 to its degree. So actually, the degree of 3 here is 5. It's a bit strange. That's why I did not want to introduce it, but good that you found it out. So every loop contributes degree 2 to the vertex. That is important. I will just write it. This is also one way to see it is because it is this, right? Every edge contributes 1 to the start vertex, not start, 1 to both the incident vertices. So loop contributes 2 to its degree, and that's how it does not also affect handshaking. No. Now the handshaking lemma is fine, right? Even if loops are there.
Okay.
Yeah, so loops we will generally not use, at least in basic graph theory. It's good to know that whenever there is a loop, you have to be careful. Okay, so the next question. So let's say I have an undirected graph G. So how many vertices can there be of odd degree?
An even number of vertices.
Why do you think that that should be the case?
Sorry.
Why do you think so? Like, why should there only be even number of vertices of odd degree?
Because the total sum of the degrees should be even.
Right, exactly. So is that something everybody can see? So what he's saying is, if you look at sum over all the degree of V, so you can think about it this way, right? So let's say you start with an undirected graph. Some vertices have even degree and some vertices have odd degree. So let V1 be the set of vertices of even degree. I'm just trying to like formalize whatever he said. Set of vertices of even degree. And V2 is the set of vertices of odd degree. Right? So this is V in 1 degree of V plus. So this we know is 2 times the number of edges. So if there are odd number of vertices of odd degree, then the sum will not be there. Okay? So essentially this sum, yeah, V2 is what, right? So the number of the cardinality of V2 has to be even. So that is probably the second pair, right? So any undirected graph has even number of vertices of odd degree. Okay. So mostly, at least for this lecture and the next, we will look at undirected graphs. Whenever directions are needed, we will bring them. So mostly you can think about simple undirected graphs, at least for this lecture and next. If there are some exceptions, then like I'll state it prior. Okay. So we defined the degree of a vertex, right? Here. In an undirected graph, we defined the degree of the vertex to be the number of edges incident on it. This should actually change. So this definition must sort of change when you talk about directions, right? For example, if you look at this graph. You cannot really say that the degree of this vertex is 3 right away. Because 3 of them are leaving this vertex and 1 of them is entering the vertex. Right? So whenever we talk about directed graphs, there is a notion of in degree and out degree. Right? So in degree of V is the number of edges that are incoming into E. For example, here the in degree is, let's do this 1, 2, 3, 4. So the in degree of 2 is 1 and the out degree of 2 is 2. So yeah, these things naturally come up in applications, right? For example, a flight network, right? How many at a given point in time, there may be flights entering the airport and leaving the airport. So you have to like say these many flights are incoming and these many flights are outgoing. So these real-time systems are actually modeled as graphs. With terminology that helps you study properties of these real-time systems. Right, so this is in the case of directed graphs. Degrees has 2 notions, in degree and out. Is this clear? So now every directed edge, if you look at it here, this directed edge, right, this one contributes a 1 to 1's out degree and 1 to 2's in degree. Right? That's how it works. So what can you say about, so let's say GVE is a directed graph. then what can you say about the in degree of V and the sum overall V, out degree of V?
Both
They
of them
should
are
be
same.
equal.
Equal, and how much should they both be?
The number of edges.
The number of edges, right? Because every edge contributes 1 to the in degree and 1 to the out. Is this clear? If there are questions, then we can take. Okay, so let's consider a simple graph. So I'll just put this as an exercise. Suppose you have a simple graph with at least 2 vertices. So there are at least 2 vertices, but there could be many. Okay. Then, how many vertices must have the same degree? Let's see, you recall. So this is an undirected graph. For example, in this, right, V1 and V2 have the same degree, 3. Can all the degrees be distinct? That is a question. It's that question. Can you create a graph where the degree of, let's say, a graph on 5 vertices, the V1, V2, V3, V4, V5, this degree?
Two vertices.
At least 2 vertices?
Yes.
Why is that? Just fill whatever you say, please.
The number of edges, the degree can be between 0 and n-1. 0 and n-1 cannot occur together. So there are only n-1 numbers to fill the n vertices.
Correct. So, so everybody sees this, right? So there is a graph with n vertices. The degree can at most be n-1 because the graph is simple. So there are no loops. So any simple graph on n vertices can have degree at most n-1. So you have n-1 many holes. So degree equal to 1, degree equal to 2, and so on, degree equal to n-1. And you have n vertices that you have to, n pigeons to put in these holes. There will be at least 1 hole with at least 2 pigeons. Right? So it's the pigeon hole principle. Is this clear? Okay. So now, before we move on to like some important concepts, let's do this problem which you had seen in earlier in one of the lectures, but in a different version. So let me just, I'm not sure if these colors are suited. These colors are not comfortable, just tell me. They look different here. Okay. So we saw this earlier in one of the classes, but I don't know if you recall, so I'll just write it down. Let's say you go to a party and there are 6 people. Then there are either 3 people who know each other, or 3 people who don't know each other. So we saw this earlier in class, right? So does anybody recall how we tried to show this?
We stated that person 1 can have either 3 or more friends or less than that many friends.
How did we like prove this? Do you like remember?
Yes, ma'am. We took person 1 and we said that person one either has more than 3 friends, or he has more than 3 people who are not his friends.
Right. So now this is the same question that we saw, but we wrote that in English. We solved that just using numbers. But now we'll try to model this as a graph. We'll try to solve it. Okay? So there are 6 people, and as is usual, we will represent these 6 people by vertices. B1, B2, B3, B4, B5. There should be one more person. I will put B6 here. Okay. And we draw an edge between them if they know each other. So maybe like V2 knows V1, V6, and V3, but he does not know V5 and V4. Right? So now the way I have drawn it, V3, V4, and V5 don't know each other. So let's suppose that V2, V6 was an edge in this graph, or V3, V6, let's say. But if this edge was in the graph, that is V3 knew V6, then we will get 3 people who know each other, right? If he doesn't know, if V3 does not know V6, we'll get another set of people who don't know each other. So this whole problem can actually be translated in the language of graphs. So what you're trying to say is that if you look at a graph with 6 vertices, there is either a triangle. So this structure is called a triangle in graphs. A graph with 3 vertices with these edges, it's called a triangle. So either there is a triangle or there are 3 vertices that have no edges amongst them. Is that clear? So when you draw them as graphs, it's much easier to actually see the proof. Something that you already saw earlier. Okay. So you can argue it this way. That's what I want to say. Something that you've seen earlier. So what we are just trying to say is, so this whole question can be replaced as in any graph with 6 vertices, there is either a triangle or there are a set of 3 vertices that do not share any edges. Okay. So these problems in combinatorics can actually be stated in the language of graph. And whatever machinery we have developed so far can be quite useful. So in the next like 20 minutes, 25 minutes we're going to see some special kinds of graphs that just come up everywhere when you study graph theory. It's very important to know that these graphs exist because they have like very special properties. Okay. So the first, so let me just write it as special graphs. So the first graph is called the complete graph. It's denoted by the letter K with the subscript n, where n is the number of vertices. So it is a simple graph with all possible edges. So what do I mean by that? Between any 2 vertices, there is an edge. So it's complete in that sense. So what is K1? It's just one vertex. K2 is K3. So can someone say what is K3?
Triangle.
Triangle, right? And then K4 is this graph. And so on. Right? So these are families of graphs. K5 is like a star surrounded by a pentagon and so on. Right? So every possible edge is there. So this graph is called a complete graph. So what is the degree of every vertex in a complete graph? Just checking.
N minus 1.
Okay. So the next graph is called a cycle. Okay. So it's denoted by Cn, where n is the number of vertices. It's just the set of vertices b1 to bn, and you have to cycle through the edges. So what do I mean by that? So v1, v2 is there, And then there is V2, V3. I should have used bracket actually. I think that's why someone had asked is their order. So when I define edge set, it should be like this. V3, V4, and so on. Vn minus 1, Vn, and then there is Vn, V1. Okay. So that's a cycle. So what is C3? So a cycle is usually defined for n greater than or equal to 3 because we want it to be a simple graph. So what is C3? 3 vertices. It's just this. And C4 and C5. So these are like super important. So one thing is that a graph can be a cycle graph, or there can be cycles in a graph. For example, if you look at K4, there are 3 cycles sitting inside, there are 4 cycles sitting inside, right? So this is a 4 cycle. This, okay, I should wait. This is a 4 cycle. This is a 3 cycle. This is another 3 cycle, and so on. Okay? So there can be cycles in graphs. So given a graph G, you can say that this set of vertices form a cycle. We will see, we will need these concepts when we prove, for example, the Euler's theorem. And so on. Another interesting graph is called the wheel graph. I'll bore you with a couple of more graph classes and then we'll move. So I actually wanted to ask one question, but I will not solve the question. I will just pose it. We will probably see like after 2-3 lectures. So this we said is K4. Okay. So what is this then?
K4, but
This is also K4, but it looks like a different drawing of K4, right? So like, are these?
Ma'am, the
Oh,
one
okay,
diagonal
okay,
is
okay.
missing.
Yeah,
Ah,
this
one
one.
diagonal,
This. Yeah, this one
Yes,
in
so-
K4.
looks like planar.
Oh, okay. So is this the first time you are hearing that term, or did you just frame the term, or have you seen this?
I mean, I've seen the definitions.
Okay, okay. Yeah. So are these 2 graphs the same? That's the question. All right.
I
They look
guess.
different. Are they same? Yeah. This we will see this after a couple of lectures. I just wanted to put the thought that it's not about the way you draw graphs actually. Right? So some people can draw K4 this way, but some people who want the drawing to look more neat can actually choose this. Right? So the question is it about the way you draw it? Or is it about the information that is encoded in the drawing? Right? The information encoded in both these drawings are actually the same. Right? So there is an edge between every vertex, every pair of vertices. Okay, this we will actually see like after 2-3 lectures. But just in case. Okay, so what's a wheel graph? So wheel graph is denoted by W and N plus 1. Right, so there are N plus 1 vertices. So it has a cycle on the outside, and then there is a vertex in the middle that connects to this. Right, similarly, it's W. And so on. So this is W4, this is W5, and so on. So W4 has a C3 sitting inside it, and so on. So on the outside, you have a cycle, and on the inside, you put one more vertex and connect it to the edges, vertices in the cycle. Okay. There is just one more graph that I want to introduce, which is called the cube, sometimes called the N cube. This is actually a very interesting graph. So it's denoted by Qn. So what is this graph? This graph is actually used to represent the binary strings of length n. So this graph represents binary strings of length n. So this is Q1. This vertex represents 0, this vertex represents 1. And if there is a bit flip, then you add a line between them. So Q2. So Qn, how many vertices are there? The number of vertices of Qn?
N plus 1.
Okay, so I should Yeah, so it represents all binary. So the vertices represent binary strings or length. So then how many vertices should we do?
2 power n.
2 power n, right? So in Q2, there are like 4 vertices. 0, 0, 0, 1, 1, 0, 1, 1. Oops. And you draw an edge between them if they differ in exactly 1 bit position. So for example, these two, right? This bit is different. These two. Oops. No, probably I wrote it wrong. Yeah. We should have written it the other way. So 0, 0, there is 0, 1. We put 1, 1 here and 1, 0. So now there is a line between these two. They differ in the first bit. This one. Right, so you put an edge between them. So 2 vertices, UV adjacent, if and only if UV differ in exactly 1 position. So can someone like try to see how Q2 is formed from Q1? Because there's some way in which you have, let's say, Q1 and you want to get to Q2. How do you do that?
A product, to take a product.
A product of what? With what? That's right, right? Some sort of a copying is happening. So for example, this 0, 1, right? If I take 2 copies of 0, 1 here, just draw it in a different color. 0, 1, 0. And put 0 in front for this copy and 1 in front for this copy and add it just accordingly, only between these. Okay? Then I will get Q2 from Q1. So one can actually draw Q4, like if you have the patience. It's a cube, to be a cube. And the vertices will be like bit strings of length 3. You can also see that after you finish drawing this, it would have been sufficient to take 2 copies of this, one on top, one on bottom, add prefix the ones on the top with 0, prefix the ones on the bottom with 1, and then add it as accordingly. So Qn has some sort of a recursive structure. That's very important, and we will use this later. If this is not clear to you, please go back and try to draw Q3 and use 2 copies of Q2 and generate Q3 from those 2 copies. Are things clear so far? Okay. So then I want to introduce one important graph class. Very important. Probably you'll see throughout this course, which are called bipartite graphs. So just as the name suggests, it's a graph where the set of vertices can be partitioned into 2 parts. Right? So something like this. So these are the vertices of the graph. And then there are some edges.
So, can we like assign some dimension to graph in the sense that if there is some like one function to R in, if like for the single for square it is 1 corresponds, including the edges, corresponds to R2, but the cube cannot be like it's not planar. But similarly, the hypercube, the Q4 won't be even able to be embedded in R3 as well. So that would require R4. So is there something as dimension of graph in general? Is there such correspondence?
So you're asking about what is the dimension of the real space in which these
Yeah.
will be embedded as planar graphs?
Yes, similar.
Well, at least, yeah, I think there should be. So, yeah, there are general theorems that talk about planar embeddings. Right? What is the dimension of the space in which they are embedded? I'm not sure if there's something particularly specific to QM. Yeah, but it is true that there are, once they do study planar embeddings in graphs. Not sure if the question is just about Q3 or Q2. Like QN cannot
No,
be
like in
embedded
general,
R,
in
is it?
for any graph, I want
Yes.
some Euclidean space which there would be direct
That is
embedding.
right. There is. There it will be planar. Right? I mean, you can embed it as a. I mean,
Yes.
this you can draw in this.
Including the
That
edges.
is. Yeah, there is this. So it's called planar embedding. I'm not sure
Oh,
if it's
planar
in this
embedding.
course. Yeah, planar embedding of graphs. And what is the dimension of like Rn in which Qn can be done? If you go higher and higher, you can actually do it.
Any finite graph will have some RNA embedding, like would the embedding will be like the finite dimension. The space, Euclidean space.
Suppose if the graph is finite. Yeah.
Yeah, for finite graph it will be okay. It is a trivial. Yes.
Okay. So yeah, some of you did not understand the remark. It's fine. We will see some portion of whatever he said. Not in full detail though, but we will introduce planar graphs. Okay. So what are bipartite graphs? You are partitioning the vertex set into two, and then there are edges between running from this part to this part. So these naturally have applications, right? For example, if you have like jobs on one side, let's say, and then there are like people on the other side, and you allocate people to jobs, there might be more people than there are jobs, or there might be like more jobs than there are people. Or you can consider this place where there are hospital beds on one side and patients on the other side. So you have to. So generally, these applications come up in allocation, resource allocation. So whenever you have a resource and you want to allocate it, you model it as a bipartite graph. So what is a bipartite graph? So that's a graph G. But now the vertex set is partitioned into two sets, right? So V is now V1 union V2, where V1 and V2 are disjoint. And there is an edge set. But what is the property of this edge set? So there are edges between vertices in V1 and V2. In other words, so E is equal to a subset of UV, where U is in V1 and V is in V2. Right? So let's just, so this is what we call a bipartite graph. So for example, let's just look at C6, right? The cycle on 6 vertices. 1, 2, 3, 4, 5, 6. Is this a bipartite graph? So what do I mean by that? Can the vertices of C6 be partitioned into two sets? So there are 6 vertices here. And the vertices of
Yeah,
C6
any
be
event cycle is
partitioned.
bipartite.
Sorry, any
Event cycle is bipartite, and if a graph contains an odd cycle, it won't be bipartite.
Okay, so yeah, let's just try to decode whatever he said. So what do you mean by a graph being bipartite? You should be able to partition the vertices into two sets such that within that partition there is no edge. Within V1 there are no edges, within V2 there are no edges, but from V1 or across V1, V2 there can be edges. So is C6 bipartite? That's the question. He answered it, but somebody else who has not seen bipartite graphs for the first time.
Yes, ma'am.
So what is
we can
V1?
consider the odd edges and the even edges. I mean V1, V3, V5, and V2, V4, V6.
Not the edges, right? You mean the odd number
Sorry,
vertices. V3, V5, V2, V4, V6. Is this clear to everybody? If there are questions, you should ask, because the whole of next lecture is going to be about bipartite graphs. So can there be graphs that are not bipartite? For example, let's say K3, right? The triangle. Is this bipartite? So what you would want to do is want to partition the vertex set into two sets V1 and V2. So you can put, like greedily just put V1 here and take V2 here. Now if you put V3 here, right, then there is an edge between the vertices of the same partition. So V3 should not go here. If you put V3 here, then again there is an edge here, right? Is this clear? So K3 is not bipartite. Okay. So now, then the question is, you're given a graph and you're asked whether it's bipartite or not. How do you identify, right? So we know that C6 is not, but C3 is, right? So K3 is the same as C3. So this should give you some hint, right? Does it? So you say a graph G. So whenever we talk about bipartite graphs, we will write G as V1, V2, E. So V1 is the first partition, V2 is like the second partition, and then there are edges. Right? So it's a tuple of three sets. G is bipartite. Finally, I want somebody to feel this. Somebody who is seeing this for the first time, just to be sure that you understand. Nobody's able to figure this out?
If for all V1 belongs to capital V1 and V2 belongs to capital V2, V1, V2 does not belong to E. No, I'm sorry. I'm sorry.
No,
I'm sorry.
Yeah, you should edit that, whatever you say.
Yeah.
Right? So he's trying to say that we should be able to partition the vertex, right, into two. That's what you're trying to do, right? How do you write that?
Maybe all cycles are of even length.
Okay, so maybe let's try to see what can you say about the length of cycles in a bipartite graph, just from what you say. So let's say, so I have to fill this up for you. So I'll just put a dash here. So suppose the graph G is, let's say, bipartite. And there is an odd cycle in G. If G is bipartite and there is an odd cycle. When I mean odd cycle, odd length cycle. So I should also say, what is the length of the cycle? It's the number of edges in the cycle. Right? So 6. C6 has 6 edges. Yeah, edges of vertices. Okay. So if the graph is bipartite, let's say you have two partitions, V1, V2, and it has an odd cycle, right? So you should have something like this. 1, 2, 3, 4. And then now, if it has a cycle, and this goes up, if it has a length, if it has an odd cycle, let's say a cycle of length 5, then there must be an edge, right, that connects this vertex with this vertex. Right? Which is a contradiction to the fact that the graph is bipartite. Right? Is it clear? Is the statement clear? So if the graph is bipartite, then every cycle has even length. Is this clear? If it had odd length, if it had an odd length cycle, then there would be an edge, right, connecting two vertices in the same partition, because there are only two partitions. Right? So now, if every cycle, let's say, so now the characterization must be sort of clear, right? So this is if and only if every cycle has even length. So we proved one direction. So now I have to say that if every cycle has even length, then G is bipartite. Let's say that every cycle has even length. So how do we argue that the set of vertices can actually be partitioned into two such that there are no edges between vertices of the same partition? So let's say that you have a graph G where every cycle has even length. And let V be some vertex in G. Okay. So now let me introduce something which I forgot to introduce. I just realized. Okay. So I will introduce that terminology and then come here. So let's look at a graph. Let's say some complicated graph. Yeah, this one. Okay. So a path in a graph is a sequence of vertices. Okay, so from V1 to V3, there is a path. So what is that path? You write V1, then write V2, you write V3. So usually in books, they write it this way. But sometimes just to make it easier to write, I will just write a path P, V1, V2, V3, and so on. So there is a path from V1 to V6. What is that path?
V1, V2, V6.
V1, V2, V6. There are also some other paths, right? You can also take this path. V1, V2, V3, V6. And there is no path from V1 to V5. So a path is a sequence of vertices. And the length of the path is actually the number of edges. So how many steps you're going to take from V1 to reach V2? 2 steps. Okay? So the number of edges is the length of the path. So now let me just complete this proof. So let's suppose that you are given in the graph you are given every cycle has even. And V is some vertex in the graph. So from V, let's put V here. So this is not, yeah. So this is a graph and V is a vertex. It need not be bipartite. For now, we have not shown that. So let me just take some graph. And there is a vertex V here. So now, depending on, so there are several other vertices. Like if there are n vertices in the graph, there are n minus remaining vertices. So you can think about, so here you had two paths, right? If you looked at this example that we saw, here there are two paths from V1 to V6. One is V1, V2, V3, V6, and the other is V1, V6. So one of them is shorter than the other. So one has shorter length than the other. So there is a natural way to define the shortest path. The shortest path is the one path that minimizes the number of steps. So V1, V2, V6, that's the shortest path. So the shortest path has length 2. Right? But there are other paths that have length 3, length 5, and so on to be there. And there can also be like two paths of the same length. Those are all possible. Right? But for any vertex V in the graph, now you can partition the vertex set into 2. Right? So those vertices such that the shortest path between V and W, between V and W, have even length. And those vertices such that the shortest path between V and W have odd length. So one thing you must remember is that every vertex falls into one of these bags. If there is no path, then that's a path of length 0 or something. There is no path. It's a simple graph, so there are no loops. So every vertex is in either V1 or V2. It cannot be in both. Right? There cannot be, like the shortest path cannot have both even length and odd length. There can be several paths. Right? But when you say shortest, you are assuming that because these are natural numbers, there is a well-defined minimum. Okay. Now we have to look at the edges. Right? Can there be edges between two vertices in V1 itself, or can there be an edge between two vertices in V2? Have we really like partitioned the vertex set? That is a question. Right? So let's say that W prime are two vertices in V1. And W prime is an edge in G. Right? Can this happen? So you know that there is a vertex V, there is W here, there is W prime here, and there is a path. Right? And you know that because these are in V1, both of them have even length. If that's the case, and if there is an edge here, right? So what do you get? If this is true, I should not draw direction here. I will just draw some squiggly line. There is no direct edge. What do you get? All right?
An odd cycle.
Right. So this means that there is an odd cycle, which is a contradiction to your assumption that every cycle in G was even. Okay? So a graph is bipartite if and only if every cycle in the graph has even length. We're talking about simple graphs. So this is like, yeah, really important. We'll use this right away next lecture. Yeah, so if there are any questions, please ask.
Ma'am, the vertex V is in neither of them, right?
So the
I
shortest
mean,
path from V to V has length 0.
Oh, okay,
Just
okay,
put it in V1.
okay.
Right? So every vertex is covered in V1 or V2. V1 and V2 are disjoint sets, and there are edges only between V1 and V2, not only across V1 and V2, not. Okay, so that's all probably for this lecture. So next lecture we will talk about an application of bipartite graphs, which is actually very interesting. So in bipartite graphs, there are natural applications that come up, right? Just as I said, jobs to people and so on. And one such application is the marriage problem, where there are men on one side and there are women on the other side. And it's very natural that men prefer some women over others, right? They may not say yes to everybody. So then the men are arranged on one partition, there are women on the other side, and men give preferences. Like this woman is fine with marriage, this is fine, but there are also some people he is not interested. So there you don't draw edges. And you want to ask, can you somehow allocate this so that everybody is happy? So such applications are studied, even like beds to hospitals, right? So some patients might prefer some beds over other beds, and so on. And even in jobs versus people, so there can be a person who knows both plumbing and electrical work, but he does not know carpentry. So you have to allocate accordingly so that all the jobs here can actually be done, right, with the people here. Right? Somehow you should like complete all the jobs, so you have to find an allocation of people to jobs. It's a very natural application of seeing computer science. You will see algorithms to do this later on, like in your final year, where you'll be given problems, like resource allocation problems, and you can write programs for this. Just like people did during the pandemic. Right? We know where beds are, we know who patients are. Some patients, and there are also like these kinds of research questions, right? Some patients are more critical than others. So they are like, they definitely need beds, but some people are not that critical. So these kinds of questions, like, there are so many applications of bipartite graphs. Right? So there's some sort of a priority. Like some jobs are like super important. So some of them, even if you don't complete, it's fine. Things like that. So these applications come up. We'll see one such application in the next class. Yeah, that is probably what I wanted to do. I already like overshot my time. Just stop the recording and then